Okay, so we'll get started in a moment. Are there any questions that we have before we begin? So what I'm going to do, and I'd like you to do this, is I'd like you to work along on your laptop. It's very important to practice these commands on the computer. So I'm going to open up an Excel spreadsheet before we start. And the default font size for Excel is kind of small, so I'm just going to highlight a rather large area here. Maybe a little bit bigger, actually. And increase the font size. 18 is good. So why don't we get started? There is a PowerPoint that you can download. If you don't have it already, that's okay. You can download it afterwards. I'm going to go into my math lab and open up the practice assignment that we're going to work on. And this will be something that will be a common practice. Every week, I'll have practice problems that are like the homeworks. They won't count for a grade, and you'll know what they are because they're called practice, and they won't be synced to Canvas. So people, don't accidentally think, oh my God, I have another assignment, right? We don't want to freak people out. So, you can only get to them through my math lab. So if you go ahead and open that up, and you might have to scroll down a little bit, you'll see this thing called Homework 5 Practice, and that's what we're going to work on today. Questions before we begin on anything, though? Just want to make sure that we don't have any loose ends. Because I have so many windows open, I'm not going to probably have the chat window open. So if you want to communicate, just speak up, okay? Because I won't have time to keep toggling this window and checking the chat, okay? All right. This week is probably the most important concept that we're going to learn the whole class. And then this is called the sampling distribution. And we're going to look at the sampling distribution for categorical variables. So we're going to be dealing with sample percentages as opposed to quantitative, where we'd be looking at sample means. And the idea behind what's going on looks something like this. And I'm going to take this little excerpt from the video summary. So you've already seen this, but I want to just go back and summarize it and put it in the context of what we're going to do today. So we talked about this poll from CNN that was asking whether or not people were going to vote for Trump. And they used a random sample of 766 people. And they got whatever they got. I forget what it was. I think it was 48%, if I remember correctly. But we all know that if they took another random sample of 766 people, they probably would not get 48. And that's because the sample percentage is a variable. Even though it's constant within one sample, it varies from sample to sample. And so what we were doing in the lecture material, we were setting up a hypothetical situation where we said, okay, assume the percentage of people who would vote for Trump in the entire population is 50%. And let's keep taking samples of size 766 over and over and over again. And we're not actually interested in the samples. Remember, we said samples estimate populations. We're interested in the sample percentage, which is going to estimate this population percentage. And so from each of those, each sample, we could compute the sample percentage and we could go ahead and plot it. And our primary objective is to understand what that pattern of estimators looks like. What pattern does it form? one of the key concepts in this class is that data does not take on values in a random manner. It forms patterns, okay? And so what we know, what theory tells us, if you learn probability theory, it tells us that this pattern is actually a normal distribution, which is cool because we just learned how to do problems with normal distributions. However, there's a few caveats. So in order to say that it has a normal distribution, we have to make sure our sample is good, which means that it's random and it's large enough. And here's some notation I'm going to let you read. The book doesn't necessarily use this. Sometimes it does, sometimes it doesn't, but you should understand that the variable here in the population, if I look at all the values in the population percentage is called pi. The sample percentage is normally denoted by p. And sometimes the book uses p when it should be using pi, but it'll be obvious from the context. Now, this is the variable. Whoops. What we're interested in is the estimator, the sample percentage. And so in that experiment that we did in the lecture, we collected a whole bunch of samples, right? We plotted them. This is a dot plot. And we computed the sample mean of the sample percentages. And I want you to pay careful attention to this notation. X bar means sample mean. Small p means of sample percentages, okay? And there's a standard deviation also. But you can see that if I did this over and over again, these data values would be fitting this normal distribution, this blue curve, which is the population. And again, there's some mean, which for the population we denote by the Greek letter mu sub p, and it also has some standard deviation, which for the population we denote by the Greek letter sigma sub p. It's very important whenever you're doing statistics, and this is a thing that will really confuse students, when you're talking about the mean and the standard deviation, you always have to ask yourself, of what? Am I looking at the mean of a population, or am I looking at the mean of a sample? Because they're very different things. And so what we're going to do today is we're going to use this rule, okay? This rule says if we satisfy these conditions, we're guaranteed that the sample percentages, that's what that small p means, the sample percentages have a normal distribution. And remember this notation. We're going to go back to what we learned before. And just as a general rule, let me make the comment that one of the things that makes this part of statistics challenging from this point on is we start to use stuff from the past. So very often in other classes, you do module 2 and then module 3 has nothing to do with module 2. Well, that's the exact opposite of this course. Everything is interrelated. Statistics is a process. What goes on in the later steps depends on the earlier steps. So notice this talk about samples being good way back in module 1, right? We're using that now. This is why. Also in module 4, we did this notation for a normal distribution. You might want to go back and review that, right? This stands for the mean, this stands for the standard deviation. And so this tells us what the population of those sample percentages look like. And again, I went through this, I won't bother to go through it because it's already in the lecture. This is one thing that I want to kind of emphasize because this is important. Every single one of you knows that larger sample sizes in general are better. We're going to see there is such a thing as a sample size that's too large, okay? But in general, larger sample sizes are better. All of you know that since grade school. None of you know why. And the central limit theorem tells us why. So the conceptual picture behind how sample sizes affect the estimators is when we have small samples, okay, remember this bullseye analogy. The bullseye is the parameter, the thing we're trying to hit, right? And these individual shots are not data values, they're sample estimates, okay? Each one of these comes from an entire sample. This is hard to wrap your mind around And the reason why is in real life, hold on a second, my headphone's cutting out. Can you guys hear me? I'm gonna ask you guys.
Yeah.
Okay, good. It just beeped. Let me go ahead and put the power in just to make sure it doesn't go out, because it becomes a real pain when that happens. Sometimes you have to shut down the whole. Give me 1 second here, sorry. Sometimes you have to shut down the whole session and start over. So you guys can still hear me?
Yeah.
Can I get an amen?
Yeah.
Hello?
Can you hear me?
Hold on, let me make sure. I just want to make sure, because I plugged it into the power source, make sure nothing wonky happened. Can somebody? I can't hear you, but if you can hear me, is your on your end, you have to make sure you unmute your microphone, right?
Yeah, I'm unmuted.
Okay, I'm going to have trouble. So let me change. Okay, we should be all right. Okay, I think I'm going to go off of this. Okay. I'm still having trouble hearing you, and it might be because, just give me 1 second here. Let me look at my, let me, okay, everything's working, okay. All right, good, good. So if it's not working on your end, I'm not sure why, because I don't have access to your machine and you guys are unmuted. Go ahead and chat, and I will check chat. Okay. All right. So here's the idea. Let me get back to this point though. The idea is that when we have small samples, each of these is a sample estimate. We can't average out the extreme values as well, in a sense, right? So we have more scatter. Whereas when we have larger samples, we have better averaging. Now, notice that when we're looking at spread, right? This has more spread, this has less spread. We know that if a sample has lower spread, it has a smaller standard deviation, right? What we really want to know is, how can we predict the standard deviation from the sample size? And so the central limit theorem tells us what the standard deviation is. Okay, this is the formula for the standard deviation. The population proportion times 1 minus it, divided by the sample size, take the square root of the whole thing. So n is the sample size. As the sample size gets larger, this ratio gets smaller, square root of it gets smaller, standard deviation gets smaller. And this is an example to illustrate this. So these are sample percentages with two different sample sizes. The red is a sample size of 25, and the blue is a sample size of 100. And you can see they're both centered around the same value, but the larger sample size has less spread because the standard deviation is smaller. That's a really important point. Okay, I'm going to start working on the problems now, but these are the key ideas that you want to know, okay? So let's go over to the problems. I won't do the first couple because they're things that I just talked about actually. These are all things I just considered. And so this first problem is giving you the population percentage. So it's saying, consider a sampling distribution. It's just a distribution of sample estimates. That's all that is, okay? Where P is equal to 14%. And by P, they actually mean pi here. They're using slightly different notation with different sample sizes. And so the sampling distribution is going to be normal. and we want to compute its mean and standard deviation. Okay. And this is where we're going to use the Excel table, okay? So go over to Excel, and we'll put this all on the same page here. And I'm going to make a little table. Now, we don't use Excel very much, okay? And the reason why is because it's not particularly good for statistics. But for repetitive calculations, it's actually really good. And this is one case where it's going to help us a lot. So our input is going to be pi and the sample size. And by the way, I want you to do this as I do this, okay? Because when you run into trouble, you can ask me for help, okay? There's a big difference between watching somebody and following it and understanding what they're doing and being able to do it yourself, right? And there's all sorts of computer things that can happen that if they happen at 1 o'clock in the morning, I'm not there. But if you ask me now, I can actually help you. So I'm going to enter a 2x4 table, and the green is going to be my input, and the orange is going to be my output. Okay. Okay. So here I'm just going to enter the value of pi, 0.14. Whoops. Put it in the right place. 0.14. Go ahead and enter your first sample size. So for my first problem, it's 4,000. Okay. Now, the mean is always equal to pi, and I could retype it, but I'm going to use an important property of Excel, which is it can link calculations to cells. So in C2, I'm saying put in C2 whatever's in A2. All right. And now I'm going to compute the standard deviation, and this is where you have to pay attention to syntax, okay? Whenever you're entering an Excel command and you want something as output, you always have to begin with an equal sign. So type equals. Excel has a number of built-in commands, and one of them is the square root function, which isn't surprising. I mean, it's more powerful than your calculator, right? So that's not surprising. And again, I could type in pi, but I'm not going to do that. I'm going to tell Excel, take whatever's in A2 and use that, and then multiply it by 1 minus whatever's in A2, and then divide it by whatever's in B2. And there's my answer. Okay. One of the things I love about Excel is you can format your answers to whatever number of decimal places you want. So if you look in the top menu, right in the middle, you'll see something called numbers. And most likely they're going to ask for 4 decimal places. So Excel can automatically round it off, which means you won't make rounding errors on the exam. Yay, yay, hooray. And there's my answer. Easy peasy. So go ahead and do that yourself and enter your values. Make sure you did it correctly. And I'm going to wait until I know that everyone's done this correctly, because this is going to be a really basic calculation that we're going to want to do repeatedly. So watch out for the number of decimal places. They're asking for 4. Whoops. And there we go. Okay. So, any problems with this? Now's the time for truth. Everybody's good? Okay. You know what? I think I just took off the mute. For some reason, it was on by default. I don't know why. not supposed to be that way, but it should be off now. So if you want to talk, Andrew, say something.
Hello?
Yep, good. We're all good. You're supposed to say something. That's an old joke. I'm just joking. Okay, so next one, same deal. Notice that when you change the sample size, nothing happens to the mean, okay? If we go back and look at this example, right? These are two sampling distributions. They come from the same population. So that means that the population percentage is the same and the mean's the center, right? So when you change the sample size, nothing happens to the center of the distribution. It just shrinks as you make the sample size larger, right? So I'm just going to type 0.14, and you're going to type whatever, your thing is, okay? Now, here's the lovely part of Excel. This is why we love Excel. Notice that while this is not brain surgery, okay, it's still a pain in the ass to type in the standard deviation. But with Excel, all I have to do is click here and just change the sample size. I'm going to change it from 4,000 to 1,000. And I want you to stop for a second and look at my screen. So look at D2. Right now it's 0.0055. Okay, after I update the sample size, watch what happens. It automatically changes. Why? Because this calculation is linked to whatever's in B2, right? I cold-bloodedly set that up so that whatever's in B2, it's going to use that value. And if I change the value of B2, I'm going to change the value of this. I don't know about you, but I think that's super cool. And this is one of the few times we're ever going to use Excel, by the way. I don't expect you guys to know it. And by the way, you don't have to use Excel. You can do all of this in your calculator. This is not particularly hard calculations, just tedious, right? And last one. And now it's just like going downhill, right? Change 1,000 to 500. If you want to type things in, sometimes it's easier to go to the formula bar. See how I'm working in this formula bar? Whenever I click in a cell, it'll display the contents here. And it's actually useful. Here it isn't really useful, okay? But when I'm dealing with something like this, a complicated expression, sometimes it's easier to work on the formula bar. And we're all done. So Excel is not good for statistics. Or not that good for statistics, but it's very good for repetitive calculations. Okay. So what effect does the sample size have on the standard deviation here? Anybody want to answer? As the sample size gets larger, what happens? As the sample size gets larger, the estimates get more clustered around the population. They have less spread. How do we measure spread? We know from module 3, standard deviation. This is the logic underlying how statistics works. So if we go back here, as the sample size gets larger, the standard deviation gets smaller. I believe that. Standard deviation does not depend on sample size. Well, that's totally false. You can see that. As the sample size gets smaller, the standard deviation gets smaller. That's not true. When this gets smaller, this gets larger. So it's going to be A. Okay, good. This next problem, but before we move on, I want to make sure, yeah, and I think you guys can speak up now. Okay, good, okay, excellent, okay. So you can speak up now, you have questions. So did everyone get that? Did anyone not get that? Let me ask it this way. Trust me, you would not be the first person, okay? Okay, good. Okay, so for this problem, they're talking about people, of the population of people who suffer occasionally from migraine headaches. We're supposed to suppose that the population percentage is 80%. That's the proportion of people who get some relief from taking certain medicine. And for any randomly chosen person, we're going to record X equal to 1 if they get relief and X equal to 0 if they don't. And we're taking a random sample of 39 people. Okay, now it's important to understand that this is the way that they're coding the data. X equal to 1 means it's our category of interest, right? We're interested in the part of the population that gets relief. And sometimes they call this an indicator variable, meaning it's indicating that the person's in our category of interest, okay? Okay, so now we're going to go ahead and answer some questions. One of the things about statistics is words matter. Okay, you have to be very careful with the wording. So they're asking us for the probability distribution of each observation. So what they want us to do is they want us to look at essentially a bar plot if we had the whole population. Okay? If we had the whole population and we were looking at one individual, which is what they want us to do. I'm just going to sketch this out really quick. So this is going to be my no, I didn't want that, but that's okay. What we're going to do is we're going to draw the equivalent of a bar plot. Okay. So these would be the people who did get relief. And, excuse me. And these would be the people who didn't. And this would be 80%, right? And this would be 20%. So this would be a bar plot, right? And so what they want to know is if I took a randomly chosen person, this is the probability distribution. If I took a randomly chosen person, what is the likelihood they would get relief from this medication? Well, these are the people that are getting relief, right? And these are the people that didn't. So there'd be an 80% chance. And this is what they're looking for in this problem. So a little bit of this is language, okay? We can throw some of these things out already because, again, they're asking us about each individual observation. And this is talking about a random sample. So in my question selections, for my choices, A and D are not relevant. So it's either B or C. And for B, the probability the medicine helps, that is they get relief, is 20%. Well, that's wrong, it's 80%. And the probability that it doesn't is 20%. So for my problem, it's C. Okay, so go ahead and try that. And I can't emphasize, one of the reasons why I do the Zoom sessions this way, and I can't emphasize this enough, but I'm not going to say this over and over again, is that you working it is how you learn it. This is how you learn to use the commands. StatCrunch is not brain surgery, but you do have to be shown a lot of these things, okay? And you could be sitting there just watching me and following, but when you do it on your own, you're not going to remember how to do it, or you may run into problems with your computer. I mean, it's kind of like when I watch boxing with some guys, right? Invariably, somebody will say, oh, you know, that boxer missed the jab. I wouldn't have missed that. It's like, what in the hell are you talking about? You wouldn't even get to that point, right? I mean, it's easy to watch somebody do something and be able to follow what they're doing, but to be able to actually get in the ring and do it yourself, you have to practice. That person had to practice to get to the point where they could do it. Same thing for you, right? It's no different. Okay, so what we know is we know that the population percentage is 80%, and that is the mean of the sampling distribution. So I'm going to type that in. And now they're going to ask me for the standard deviation. Now I'm going to say something, and the book gets sloppy on this, okay? But you shouldn't be, because sometimes they aren't. So they're kind of two minds, you might say. You have to make sure that you satisfy the conditions of the central limit theorem, okay? We generally assume the sample is random, unless there's evidence that suggests that you have a biased sample. But we also have to check the sample size. And so if I was to do this in my problem, okay, and the book gets sloppy on this, okay? So my n is 39 and my pi is 0.8. And what I have to check here is I need to check that n times pi is greater than or equal to 10. So this is roughly 40 times 0.8, so that's 32. That part's okay. So here, pi times n is about 40. It's a little bit less than 40. I'm sorry, a little bit less than 32. So this is greater than or equal to 10. However, if we check the other condition, n times 1 minus pi, it's not satisfied. So 39 times 0.2 is roughly around, it's a little less than 8, right? So this is less than 8, which is not greater than or equal to 10. So the book is wrong. You should not be using the central limit theorem. So they get sloppy sometimes, okay? But then sometimes they'll explicitly ask you to check it, okay? But you should always check it. Here they don't. Okay? So we're just going to compute the standard deviation. So I know that my population proportion is 80% and my sample size is 39. And you're just going to change your numbers in your problem. And there's my standard deviation. And again, notice how it's nicely rounded to 4 decimal parts. I mean, so using Excel is a huge, you don't have to, but you know, it's so much easier, right? Okay. And we're good. So again, this is really important, okay? Because down the road, you're going to find that taking time and thinking about things is going to help you a lot. Standard deviation of what? Okay, this is the standard deviation of this guy here, this blue curve. This is a standard deviation of the population of sample percentages, okay? One of my stats teachers used to say the most dangerous word in statistics is the word what, and he's right. Mean of what? Standard deviation of what? Notice we have all these different things running around. We have to keep them straight. So this is the standard deviation of the sampling distribution. Sampling distribution sounds like an esoteric thing, but it's just the distribution of what we get from samples. It's a distribution of sample estimates. That's all it is. Most words in statistics sound like what they are, which is really cool. That's what I love about that. I'm not going to bother doing this because we just did this in the last problem. You can go back and watch what we did in 5, and you can do 6. So we're all okay there. Okay, this is asking something that, again, we have to go back to module 4 to understand, okay? I'm going to go ahead and pull up the PowerPoint from module 4. And we talked about z-scores, and we talked about the empirical rule, which, you know, you may or may not remember, but it's actually worthwhile memorizing, or at least knowing, okay? Because we're going to use it a lot. What the empirical rule tells us. It says when you have a mound-shaped distribution, it tells us the likelihood that you're going to get a data value a certain distance away from the mean, okay? And by the way, when you're working with a normal distribution, the empirical rule becomes very, very well followed. It almost becomes exact. So remember that 99.7% of the values are within 3 standard deviations of the mean. So it wouldn't be unusual to find a value 3 standard deviations from the mean, because 99.7% of the population is there. However, it would be unusual to find a data value more than 3 standard deviations, because there's only a 0.3% chance, right? And in fact, if you remember how the box plot flags outliers, it's actually doing something very similar to this. It's saying that that data value is unusual because it's too many standard deviations from the mean. I won't go into that, but that's kind of what it's doing. Okay, so this is what this question's asking. We're going to say a data value is unusual. Okay, so we're going to say that a data value from a normal distribution is unusual. In other words, we're not likely to get it if it's more than 3 standard deviations from the mean. Okay? So I want to make sure before we go on, everyone is kind of good with this logic, that this makes sense. So this is one of the ways that we define whether or not a data value is unusual. We're going to use this a lot, okay? Notice that this is the same as saying that the z-score, which tells us the number of standard deviations we are from the mean, the z-score is greater than 3. And we're going to see 2 weeks from now, when we start working with hypothesis tests, we're going to come back to this fact. So again, everything's interrelated, right? Okay, so what we're going to do here is they told us the standard deviation and they've told us the percentage. So I'm just going to add and subtract 3 standard deviations, okay? You can do this in StatCrunch, doesn't really matter. So this is the mean. This is standard deviation. This is 3 standard deviations below the mean, 3 standard deviations above the mean, and we're just going to compute those out. And the only reason why I'm using StatCrunch, you might say, I'm using Excel, is because we're going to do this sort of problem more than once, right? And you can go ahead and type in whatever your standard deviation is. And now we're going to use Excel. We're going to say, Excel, use whatever's in this box for the mean and subtract 3 times whatever is in this box for the standard deviation. Okay. And now we just hit enter. And I really don't have to do anything else because I noticed that there's only one value, okay? But I'm going to do the other one, okay? And all you can do is you can click here, go up to this bar, and cut and paste it, Control X, Control V, hit enter, and then go here, paste it in the menu bar, and change the minus to a plus. And I can do that just to check myself, right? These are only to 3 decimal places, so I'm going to round down. And sure enough, there's only one thing that will work. Okay? So that's the definition of unusual. That's what they want you to do, okay? Suppose you got a sample proportion of 71%. Would that be unusual? Yes, it would be, because it's outside this 3 standard deviation range, right? So it lies outside this interval. Okay, good. Okay, I want to work 2 more problems, and these are the ones that on the homework will give you trouble, okay? I work a few more problems on the video from Thursday's class, but if you get all this, you'll be fine. Okay, a baseball player in the major leagues, he usually has 500 times at bat in a season, And suppose he's a 305 hitter. Okay, so if you were an omniscient being, God, okay, this is pi. This is what he actually would hit. His batting average is a sample because it's a sample of all the at-bats he could have had, okay? It's a sample proportion. So what they want to know is, in a season, if he bats 500 times and his actual batting average, his real batting average is 305, what are the possible batting averages that he could actually get in a season? Well, this is a sampling distribution. So the distribution is bell-shaped. Well, they all say that. The mean, which is the true value, is 305. Well, there's only two of these. And it has a minimum of 0 and a maximum of 1 standard deviation. Well, that doesn't even make sense, right? So this has to be the correct one. We know that 99.7% of the values lie within 3 standard deviations. So that's our answer. Okay. So now they want you to answer why or why not these would be unusual. So all I'm going to do is I'm going to change the mean and standard deviation and compute these values again, right? So for my problem, this would be 305. You're going to change whatever it is in yours. And the standard deviation, we're told, well, we're going to have to actually compute that out. So I actually have to go here. They don't give me the standard deviation, or do they? They don't. So I better compute it. .500 at bats. And there's my standard deviation, and I'm going to copy it. And I'm going to paste it as numbers. Let me copy it again. I cleared it, sorry. Copy. And I'm going to paste it as a number, okay? Not as a formula. Okay. So how do I determine if these are unusual? Well, they have to lie outside this interval, right? This is the 3 standard deviation interval right here. Okay. Do they? No. Okay. 0.284 is in this interval, and 0.326 is also. So they would not be unusual because they lie in here. B is wrong because it says they're extremely unlikely, and we know that's not true. They're extremely likely to lie in a 3 standard deviation interval. And these are not 1 standard deviation from the, oh, hold on, I have to actually go back. These might be 1 standard deviation from the mean. So let's compute the z-score. Let's just make sure. So I'm going to make another. They might be 1 standard deviation from the mean. We don't know that. So what I'm going to do is I'm going to take the data value, which is 0.284, and I'm basically going to compute its z-score, right? And subtract off the mean and divide by the standard deviation. And sure enough, it's about 1 z-score below, right? And again, copy and paste this, go over to here. Yeah, and I'm just going to say plus. But I'm also going to have to change this value too, right? I'm going to have to change this to 326. So again, I'm just computing the z-score, and I get +1. So it's actually C. And we know for 1 standard deviation away, we're actually very likely. Okay, 68% of the data is in here. So it isn't unlikely to get that data value. Okay. All right, good. minimize this here. I gotta be careful how I do this. I can't minimize while I'm recording. Give me 1 second here. But I can do this. I'm going to let you do this. This is actually the handout. I mean, this is actually the Zoom thing which I posted. This problem is actually this one. What did I do? Where did I do that? Right here. Sorry, right here. This slide right here that we've already discussed answers that particular problem. So you guys know how to do that one. We've done that sort. And so I want to do one last problem that we're going to be using StatCrunch, okay? So this will be the last problem that we will do. This is a taste test where there's a 50% chance in the population a person can't distinguish brand A from brand B. And we have a random sample of 200 people. So it's kind of like the Pepsi Coke challenge, right? So the problem. Oh, the screen share went off. Thank you. Sorry about that. Let me go back. Thanks. Okay, excellent. All good?
Thank you.
All right, thanks. I appreciate that. Okay, so here, there's a 50% chance a randomly chosen person can't distinguish. They do like the Pepsi Coke challenge with 200 people. So I can already start computing a lot of things, right? I can go to my Excel table. I know this is 50%. Oops, I got the wrong one. I gotta go up here, sorry. 50%. My sample is random. It satisfies the condition that n times pi is greater than or equal to 10. And there we go. Okay. So this is the mean and the standard deviation for the sampling distribution right here. Okay. So now it's asking me, what is the likelihood that just one random sample has a percentage between 50 and 55? And this is where we're going to do StatCrunch with the normal calculator. This is the part that can be kind of tricky. So we're going to go to StatCrunch, and I'm going to go to calculator normal. Okay. And now I'm going to type in this mean and this standard deviation, right? So if I go over to here, my mean is 0.5 and my standard deviation. And sometimes it helps to use more than 4 decimal places. So sometimes it can be a little sensitive. So I'm going to actually increase it to 6 just to be careful, okay? So make sure I get it right, 0.035355. And so I want to calculate the probability that I'm between 2 values, and it's 50% and 55%. And so we did these calculations back in module 4. This is just a normal distribution calculation, right? And that's my answer. And then again, StatCrunch is kind of cool because you can just copy and paste, and you're all good. And the rest of them are just kind of variations of this problem, okay? Okay. And this is a good one before we end. This is a good one to make sure that everyone is on the same page, because this is a calculation that really can kind of throw you off. And now what they're asking for this last problem is they want the values that bracket the middle 90%, okay? So here's what they're asking for the last problem. they have a normal distribution, right? And what I'm going to do is I'm going to use my normal calculator. I want the values that are going to contain the middle 90%, right? Well, I'm going to use symmetry here. If this is 90%, under the whole curve is 100%, right? So there's 5% in each tail. So this means this is the 5th percentile, the lower limit of that interval, and this is the 95th percentile. And so you're going to go back and you're going to use StatCrunch, where now instead of inserting a data value, you're inserting a probability. So you're going to use StatCrunch, and again, you can go back to module 4 and check this out, right? But I'm going to enter standard, and I'm going to put 0.05 here for the 5th percentile, and it will give me the data value that I need. And then do the same for the 95th. So again, we're all kind of building on stuff that we've learned before, and we're going to continue to do this. So you might want to go back to module 4 and kind of review a few of these skills. So that's pretty much all for today. I'll put this video up online later this afternoon. If you have any questions, feel free to ask me, and of course, Anna has her SI on Sunday. So, but I'm hoping this will help you through the majority of the problems. Any questions before we call it a Friday? Everybody's good? All right. Well, hey, have a great weekend, and I will talk to you soon. Take care.
Thank you, you too.
All right, bye-bye.